Hey there, students. In 6.4, the central limit theorem is introduced, and basically it tells us how to work with the mean value of a population and the standard deviation of a population when trying to look at probabilities of the mean of samples instead of an individual. And so it's kind of heady. So I'm going to do a sample problem from 6.4 that tries to illustrate through the doing of the problem the difference between what we were doing before the central limit theorem and what the central limit theorem allows us to do afterwards. And so I've pulled up number 11 from the homework number 8, which is on section 6.4 and 6.5. Problem 11 is from 6.4. So it states as follows: an engineer is going to redesign an ejection seat for an airplane. The seat was designed for pilots weighing between 120 and 161 pounds. The new population of pilots has normally distributed weights with a mean of 130 pounds and a standard deviation of 30.7 pounds. So there's a couple of parts to the problem that we want to do. The first part is asking us if a pilot is randomly selected, the problem wants us to find the probability that his weight is between 120 and 160 pounds. So this does not use the central limit theorem. We looked at this in 6.2 already. So let's go through and remind ourselves how we would do that. And then in the next parts of the problem, we can see what's different when the central limit theorem is applied and how we do things differently. Now, they do give us access to the tables of values, but I've already pulled up StatCrunch here for us to use StatCrunch. So again, when we are looking at the probability of a randomly chosen value from the population falling in a certain range, and we know the standard deviation and the mean value from the population, we go to Stat Calculators and we pull up the normal calculator and we get this nice graph. So the mean value for our population now is 130 pounds as stated in the problem, and the standard deviation is 30.7 pounds. And we are supposed to calculate the likelihood of being between two values, between 120 and 161. So I'm going to switch over to the between version of the calculator and give a lower value of 120 and an upper value of 161. So then the normal calculator will show us the graph, and it'll show us the region under the density curve, and it shows us that there's about a 47% chance of a randomly chosen member of the population being in that range when the population has a mean of 130 and a standard deviation of 30.7. So they want that to 4 decimal places. So I'm going to grab that to 4th decimal place, and it looks like I need to round up the 3 to a 4. So that would be just like a problem we would do before we introduce the central limit theorem. So in part B, it modifies the requirement a little bit. It says if 36 different pilots are randomly selected, find the probability that their mean weight is between 120 and 161. So what's different? In part A, we are randomly choosing a person from the population, whereas in part B, we are taking a sample of people from the population of 36 people, and we are looking to see that the mean of our sample is within that data range. And the central limit theorem says that we would do everything the same way we did if we were taking an individual, but when you are taking a group, that gives you a different standard deviation than the individuals from the population would have. And that the way we modify the standard deviation from the population, if we're instead choosing a group of a sample size from the population, is we divide the standard deviation for individuals by the square root of the sample size. So in this case, the sample size is 36 different pilots are being sampled, And so instead of a standard deviation of 30.7, we would have 30.7 divided by the square root of 36. Now, the square root of 36 happens to come out nicely to 6. If it wasn't such a nice number, we could just use the square root on the calculator to get the square root value, even if it's not a whole number. But to get my new standard deviation for a sample, I'm going to take the old standard deviation, and I'm using the calculator to do this, 30.7. And then I'm going to divide that by the square root of the sample size of 36. So I'm going to divide by 6. And so now when I'm looking for the likelihood for the mean of an entire sample to fall in that range, this is my new standard deviation. It's much smaller. Instead of 30.7, I have a little bit more than 5. So I'm just going to grab a bunch of that and copy it in here. And now that's my new standard deviation is 5.1166666. And then I do the same tool with the same calculation, but I've adjusted the standard deviation because I'm now looking for the results for the mean of a sample of 36 instead of just an individual. So now there's a much greater likelihood because the standard deviation is smaller, and so without as much deviation, it's harder to get a whole group to deviate from the mean value as it is for an individual. And so my probability now for the whole mean for the sample of 36 people has gone up to over 97%. To 4 decimals, I need to round up the 6 to a 7. But now we're talking about there's a 97% likelihood that the average of a big sample of 36 pilots would fall in that range, where it was less than a 50% likelihood that an individual would. So that's what the central limit theorem does for us. So in the last part, they want us to sort of put this together logically a little bit. So it says, when redesigning an ejection seat, which probability is more relevant? Well, an ejection seat is just going to hold one person. It's not going to hold 36 people that have some average value needing to be correct. And so it would make more sense to look at the likelihood of an individual chosen being in the effective range of the ejection seat than it would for a group of 36 to have an average in that range. So I'm going to choose that the part A calculation for an individual is more relevant. So let's see, part B, no, part A, so that's either B or D. Part B says part A because the seat performance for a single pilot is more important, which sounds correct, whereas part D says part A is the choice because a sample. No, so that's the wrong one. So I would choose B here to finish the problem. All right, so hopefully this was helpful. The key thing to recognize is we're still using the same tool that we did before we were talking about mean values of samples. But when using that tool, you need to use the central limit theorem to adjust the standard deviation from, instead of being the standard deviation for individuals from the entire population, when you choose a sample of 36 from that population, then the sample size affects the standard deviation by taking the individual sample standard deviation and dividing it by the square root of the sample size to get the new standard deviation for samples of size 36. I hope that helps. Keep up the hard work and reach out to me if you need help in any way.